Hello, my name is Siddhant Arya. This is the presentation for state design pattern. In this presentation, we will discuss different aspects of the pattern and finally look at an example application which implements this pattern. In the beginning, we shall see some background of state design pattern followed by its intent, motivation, applicability, and consequences. Further, we will compare state design pattern with strategy design pattern. During the app demonstration, we will see the UML class diagram of the application, pseudocode, and the application demo. Finally, a brief on lessons learned and best practices, followed by the conclusion. Design patterns are broadly categorized as creational, structural, and behavioral patterns. State design pattern is one of the examples of behavioral patterns. This slide shows different patterns that come under behavioral category. The intent of these patterns is to distribute the responsibility and behavior in an efficient and safe manner. The patterns follow open-close principle by identifying common behavior among the objects. Following the principles of behavioral patterns, the state design pattern intends to allow an object to change its behavior when its internal state changes. The internal states in this context refer to the state changes due to the change in the attributes associated with an object, whereas external state change may refer to the environmental changes that affect the object state. The state design pattern receives its motivation from the need to support dynamic behavioral changes in an application. It helps to avoid lengthy switch case statements and helps to establish open-close structure. This pattern can be applied when an application needs to support situation-specific behaviors. Each set of the behavioral aspects can be called as state with respect to the context. As a consequence of using this pattern, classes can be separated from the state-specific behavior. It can eliminate switch statements by providing a framework to manage the behavior of the application. The pattern follows open-close principle, which means the application design is open for extension but closed for modification. This slide shows the comparison between state and strategy design patterns. Firstly, both the patterns are similar in terms of following open-close principle. Also, both patterns use derived classes to control the behavior. Intent-wise, state pattern manages different states of an application, whereas strategy pattern provides an interface to multiple options of strategic algorithms. Every state holds a reference to its context, but strategies don't. Similar to finite state machines, in state pattern, each state defines relationship with other similar states, like successor or predecessor. However, strategies are independent of each other. States define what can be done based on the context, whereas strategies define how something can be done based on the context. The state transitions can be conditioned and controlled using events. In case of strategies, a user needs to select one option from the multiple. Finally, the slide shows examples of both the patterns. This slide shows the basic UML class diagram for state design pattern, where context defines an interface to client to interact with the states. State defines interface to the concrete state classes, and concrete state implements the different states of an object. This pattern is well demonstrated in the example application discussed in further slides. The demo application implements gear states of a vehicle, such as park, reverse, neutral, drive, and sports. Referring to the UMS diagram in this slide, there are two different instances of state pattern, one applied for vehicle state and another for gear state. Let us consider vehicle state as an external factor and focus on gear state, which determines internal state of the object gear. At the top level, vehicle acts as a client. On the right hand side, gear entity acts as a context for gear state. Gear state defines an interface to different states of the gear. At the bottom right, concrete classes are shown which implement the gear state interface, which are gear reverse state, gear park state, gear drive state, gear neutral state, and gear sports state. In similar fashion, on the left hand side, vehicle state defines an interface to different vehicle states. The interface is implemented by concrete classes vehicle in stationary state and vehicle in moving state. In further slide, we shall see the implementation details. The client has main function which creates vehicle object and instantiates the user interface of the application. Vehicle class has instances of gear and vehicle state classes, which are interfaces for the concrete states. Possible states for the vehicle and gear classes are represented as enum. Class vehicle state provides an interface which is implemented by concrete classes vehicle in stationary state and vehicle in moving state. Class gear stores a reference to concrete state objects and delegates its all state related behaviors. Gear works with a state via the common gear state interface. Gear state declares the common interface for all concrete states. It declares methods that make sense for all states. But each state will provide state-specific implementation. For example, gear park state implements the behaviors specific to park state. Other gear states are implemented in similar manner. In this slide, at the top, it shows application UI for user actions. A user can change the vehicle state using the given radio buttons and can change the gear state using gear buttons PRNDS. The application shows appropriate messages for state transitions. in the text area as shown in the bottom two figures. Coming to the demonstration of app, let us follow this table to check the behavior of the application. First use case, as soon as I start the app, the default states are set. Vehicle status is set to stationary and gear status is set to park. Changing gear state from park to reverse when the vehicle is stationary is a valid transition. Thus, the gear status is set to reverse and the message is shown changing gear from park to reverse when vehicle is stationary. Next, while changing the gear from reverse to sports when the vehicle is stationary is an invalid state transition. Thus, there is no change in gear status. And that's why S is not highlighted in red. And the message box says transition from reverse to sport is not possible when vehicle is stationary. While changing the gear state from reverse to neutral when the vehicle is stationary, it is a valid state transition. And that's why neutral is highlighted. While changing state from neutral to drive when the vehicle is moving is a valid condition. Next, while changing the condition from neutral to sport is also considered as valid state transition. And finally, changing state from drive to sports when vehicle status is moving is a valid condition. As we observe, state transitions are controlled by the current gear state and guided by the possible state transitions. We can add any number of states to the gearbox without changing other states. In brief, lessons learned are the state pattern is similar to finite state machines. Hence, state explosion is more likely in large programs. To identify transition events and conditions, clear understanding of the problem domain is needed. Introducing number of external parameters increases the complexity of the state transitions. A well-defined context and states derived from abstract base class result in a flexible solution. Best practices, solid understanding of the states is a key requirement, and modifying states in later stages needs much more effort. Using dependency injection for external parameter is always helpful. To conclude, state design pattern is useful when it comes to managing a state-driven application. The pattern effectively manages internal states and provides interface to extend more states. However, large number of states may result in state explosion and ambiguity. Clear understanding of the domain is necessary to identify correct states, transition events, and external dependencies. As the complexity of the design increases, the chances of design being anti-pattern are more. Thank you.